So I'll see the probability distribution now. Before getting into actual things, I will again go with my regular technique that I will write down one example. We'll see what is happening in the example. And when all these things are done, then we will define the terms. So my experiment is tossing a coin thrice. So depending on this, I will have a sample space in which I will have head, 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 then head, head, tail, head, tail, head, tail, head, head, then tail, tail, head, tail, head, tail, head, tail, tail, the last one. Tail, tail. This is my complete sample space. Now what I will do here is I'll define a function. I'm defining a function, say call that the function is x, which is from this sigma to the set of real numbers. How I am defining sigma of an element small x is equal to number of heads in x. So what will be sigma of h? Oh, sorry. I've written this wrong. It has to be like x of small x, capital X of small x, the number of heads in x. Where does this x belongs to? X belongs to your sample space. So I'm defining a function from my sample space to the real numbers. And how I'm defining it? How I'm defining it? I'm defining it as the number of heads in that element. So what will be this capital X of h? Anyone?
So that would be 1.
3.
1, 3. Then X of h t, which will be equal to X of h t h, which will also be equal to X of t h h. This is equal to.
Sir, but the number of heads, 3 heads in a row is just 1. Probability is 1.
No, no, we are not calculating probability. I have defined a function from the sample space to real numbers. That's
Yes,
it.
sir. So that's why we have, if we are
And
having 3h, then it will be 3.
yes,
Sir, I didn't get it.
three. What is the problem? I mean, I'm not able to understand because you yourself said that HHH is uh, 3. I mean, what you're not understanding.
So what is 3 basically? I'm just asking that.
Number of heads. If you take an element from this,
Yes, sir.
x of that element is equal to number of heads. So if I take x of head, the number of heads are 3. That's why
Okay,
x of
okay.
HHH is
Got
3.
it. Just I was thinking that having having HHH simultaneously is just 1. So that is in sample
No, no,
space what I'm getting.
no,
Okay,
no.
sir, got it.
Huh. So the next one, x of TH is equal to x of THT is equal to x of HTT. What is this? 1. The last element is remaining TTT. What is this? This is going to be 0, right? So I started with an experiment. I have a sample space, right? Then I have defined a random variable. What is this called? This function that I have defined, this is called the random variable. So yes, anyone, what is a random variable? Can you define the random variable from this experiment now? What is random variable? If someone asks you what is random variable, from this complete example, can you define the random variable? You're not getting what is this random variable? I'm saying that x is called the random variable. What is x? In short, you need to define x. What is x?
So x is the function.
X is a function. Exactly. So it is a function from the sample space to the set of real numbers. So what is a random variable? Random variable is actually a function from the sample space to the real number. Now, what is the use of this? Now, what I'll do is I'll find out the probability of x equal to 3, say. What is x equal to 3? For which points do you have the value of x as
For
3?
h h h.
Only one element is there who is having 3 as the value of x. What will be the probability? So, number of elements with x as 3 upon total number of elements. How many elements do you have the value of x as 3 in the sample space?
One.
So
One.
that 1 by
Eight.
8.
8. So I can also assign the probability for x equal to 2. Now can you tell me what will be the probability?
3/8.
3/8.
Exactly. Very good. So probability of x equal to 1.
1/8.
No,
How
sir, that
many?
is also 3/8.
That is also 3. Right. The reason is there are 3 elements with value of x as 1. Right. The last one, probability of x equal to 0.
1/8.
1 by 8. So what we have got now? So I can make a table from this. How can I make the table? I have the random variable x, which is taking the values 0, 1, 2, 3, 4. Oh, there is no 4, only 3. And then I have another row which tells me p, the probability, p of xi. At 0, the probability is 1 by 8. At 1, probability is 3 by 8. At 2, the probability is 3 by 8. And at 3, the probability is 1 by 8. What we have got? For each value of your random variable, I am getting a probability. So this distribution, what is the distribution? Xi, comma, p of xi. Have you seen this kind of thing earlier in statistics? That was
Yes, sir.
that was frequency distribution, if you remember. So there was this certain observation and the number of time that observation is repeated. That was called the frequency distribution. What will this be called? The probability distribution. So you have distributed the probability over what? Over what you have distributed the probability? Values of so difficult. Over what you are distributing the probability. You have the total probability as 1. Over what you are distributing it?
That X random variable.
Uh-huh. Exactly. So you are distributing the total probability into the random variables. Okay. So this type of distribution. So I have covered everything that we are going to learn in this chapter in one example. So you have the random variable first of all. Random variable is actually a function from the sample space with a set of real numbers. There's just one variable which is assigned here, so that makes it univariate as the name suggests. Then whatever different values of x it is taking, for each value of x, I have certain probability, and you have this probability distribution. What will be the summation of all those probabilities? That is 1. So that's why the univariate probability 1 is distributed over all the random variables. So we will write down this. And then we'll see what are different types of random variables, and depending on the different types of random variables, we'll have different types of probability distributions. Fine. Let's write down the definitions now. Let
Sir,
yes,
means for a univariate distribution, we just need to deal with
one
only one
random variable.
random variable. Okay.
We'll see some examples where we have bivariate probability distribution. Won't go into details of it, but we'll surely see some examples. Let sigma be a sample space. Corresponding to a random experiment. Corresponding to a random experiment. A function x from sigma to the set of real numbers where R is the real line is called a random variable. So there are two types of random variables. Say if the random variable takes discrete value, just like in this example, it was taking just 0, 1, 2, 3, and 4. Okay, so these are discrete values. Such type of random variables are called discrete random variable. Say if I have a population in study and so my sample space is the people living in Pune. Living in Pune. And I'm defining the random variable from sigma to r as x of p is equal to the weight of p. It is a real number. I mean, you can simply agree to this. Weight is a real number. So every person I take, and I'll find out its weight, his weight. So I have a random variable, but in this case, will it give you discrete values? 1, 2, 3, 4 like this? Or it will be something else? Be quick, it is not so difficult so that you need so much
So
time to
values
think.
will not be discrete.
Will be discrete? You sure?
No, sir. No, sir.
No. So what can I say about this random variable? It will take the values in an interval. Say 0 to 400. Can I say that x will lie always between 0 to 400 or there will be someone of 500 kg? Maybe. So if you want, we'll take it 1000 kg. Surely there won't be anyone of this. So this random variable takes the values in this interval. So this two are different types of random variables. The one which takes the discrete values is called the discrete random variable. The one which takes the values in an interval is called the continuous random variable. So we will study the probabilities for both of the types. So there are two types of there are two types of random variables. The first one, discrete random variable. A random variable x is said to be discrete. A random variable x is said to be discrete if it takes if it takes finite or countably infinite number of values. So for an example, one x could be of the form omega 1, omega 2, omega 3 up to omega n. So in whichever cases x takes the values from 1 to n, that is a discrete random variable. Any other type? Which is the other type which can be considered countably infinite? Can you tell me a set which is countably infinite? Can you define a set which is countably infinite?
Set of whole numbers.
Set of integers.
Set of integers. So this will go from omega 1, omega 2, omega 3, up to omega n, and dot dot dot. It will go on increasing. Even this kind of random variable, the discrete random variable. The second one,
Uh, sir,
yes,
sir means in the first example of a discrete random variable, the values won't go beyond omega n, right?
yes, this is a finite set, but this is countably infinite.
Okay.
Continuous random variable. A random variable x is said to be continuous. Is said to be continuous if the range set of x is an interval or union of intervals. So for an example, just now I said that weight of a person, the values will be in an interval, weight of person. Second, any other example? Don't say height, go in some
Income
other
of
domain.
person
Income of a person,
working in a.
but that can be countably infinite, right? No
So
one can. Okay,
if we
anyway,
define it
consider it
in a
uh,
certain
interval.
means,
But
yes,
no one can earn like 1 rupee and 10 paisa, or even less than 0.01 paisa, like in that
yes
manner.
sir.
Yeah.
Sir,
Yes. Go ahead, Saurabh. What is the problem?
okay, okay. I'm not sure whether we can use this example for continuous random variable, but can we take drilling, the depth of drilling to find oil? Means it is continuous,
Uh-huh.
that's why.
Yes, yes, yes. That could be
Okay.
an example. So consumption of electricity.
Sir, saving of water from the raindrops can be come under this.
Yes, yes, exactly. That will also work. So what is the difference between two of them? Uh, the range is set. I mean, the major difference in both of them is the range set. What do you call a range set? If you have a function from x to y, capital F from x to y, what do you call a range set? f is a function from x to y. What is the range? So, you have given JEE, CET, and there are a lot of questions in JEE based on this. You are given f is a function from R to R, and you are given f of x equal to x square. What is the range of f of x?
So that is 0 to infinity.
0 to infinity. Exactly. Why?
So the value of the output that we are getting by putting any value of x from function
Exactly.
that is 0 to infinity.
Yes, exactly. So, whatever the possible values are, that is called the range set for a function. So, for a discrete value, the outcomes are always, yeah, I mean, like this, the first set or in the second set. Whereas, when we are talking about the continuous random variable, my range set is an interval or the union of interval. There's a major difference. So when I'm talking about the probability for discrete random variable, I can talk of a probability at a point omega 1. But when I'm talking of continuous random variable, what is the probability of say 0.001? Can I talk of it? So this is a major difference. In continuous random variable, I don't have the scope of talking of probability at a certain point. I can always talk of probability in an interval. Okay, remember this. When we have a continuous random variable, I can talk of probability in an interval, not at a certain point. But when I'm working with discrete random variable, I have the scope of talking about the probability at a certain point. Fine. Once we have defined both of them, now we will look at the probability distributions for each of the case. We have already done the probability distribution for each value of x. We have defined the probability in the first example itself. Just for revision, I'm going up again. So I have defined the random variable. I've got the values of random variables 0, 1, 2, and 3. For each value of x, I have the certain probability. And I said that this is called the probability distribution. Now, when we are having a discrete, random variable, we can assign a probability mass function. Probability mass function. Let x be a discrete random variable defined on a sample space sigma. Defined on sigma. Suppose the set x1, x2 up to xn is the range set. Is the range set of x. Then we assign a number. Then we assign a number p, which is nothing but the probability of x equal to xi. It's called the probability of xi. Called probability of xi, such that the first condition, probability of, or simply pi, let's use this nomenclature and fix this. Pi is greater than or equal to 0 or I is equal to 1, 2 up to n. And the second one, summation pi, I is running from 1 to n, is equal to 1. Then the function p, then the function p as defined above, as defined above, is called probability mass function. And it is abbreviated as PMF of x. The table containing values of x, values of x along with the probabilities is called probability distribution. A lot of MCQs can be made here. How? A table, I can give it to you and verify whether the given is a probability distribution or not. What will you do? Xn, and you have the probability of x equal to xi as p1, p2 up to pi. How can you verify whether this is a probability distribution or not? Or you cannot verify. Okay. Anyways, is the definition clear? Once we go for example, these things are going to be clear. Is the definition clear to you? What do you call a probability mass function? Someone respond to this. What will you call a probability mass function? Be quick, it is not so difficult. I don't want to call out the names and follow the regular procedure. Please be quick.
Sir, in probability mass function, it gives the probability that discrete random variable is equal to the value. Means in if xi is equal to pi, like that.
Okay. Sakshi.
Yes, sir.
Yes, what is probability
Probability
mass?
should be equal to 1
It is probability
and probability should be equal to 1
equal to 1. Probability should be equal to 1. Okay.
Sir, it should be greater than 0 and equal to also, maybe.
Well,
Probability mass function, the word itself says that it is a function. It takes the input from the range set. Okay, so it is a function from the range set to the interval 0 to 1. Okay, now the probability mass function, what it is going to do? Probability mass function will assign a probability to each random variable. Okay, and it should assign the values and it should satisfy two conditions. What are the conditions? That each value should be greater than or equal to 0 and summation of all the values, whatever it has assigned to the random variable, is equal to 1. Such a function is called the probability mass function. Second, what do you call a probability distribution? When you arrange all these values with respect to the random variables in a proper table, this is called the probability distribution. I hope it is clear now. Let's go for an example. A pair of fair dice, a pair of fair dice is thrown. Let x is equal to sum of numbers of sum of numbers on the uppermost face. Uppermost face. Find the probability distribution. Find the probability distribution. Yes. What are the different values of, you have the experiment. What is your experiment? Your experiment is that you are throwing a pair of dice and your what is your random variable which will be from the sample space to real number? It is equal to sum of from the uppermost cases. What are the different values of x that you will get? What will be the range set for x?
two. It will start from 2, 3, 4,
Yes, exactly, and it will go up to
maximum
12.
12. 12 only. Yeah, 12 only.
9, 10, 11, and 12. We need to find the probability distribution. What is probability distribution? That is the table. For every value of x, you have certain probability. And for each value of x, you need to make a table which will have the values 2, 3, 4, 5. And I need to give the probability for 2 probability of 3, probability of 4, and so on. So I'll make a table now here. Okay. So what I'll do is I'll write down the x here. And in the last one, I'll give the probability. So I will have x here, the possible value of x, and elements of sigma, which are going to give me this value of x. And then I will have pj, which is probability of x equal to j. 2. How many elements are going to give me the value of x as 2?
1,1.
1, 1.
1.
1, 1. What is the probability?
1 out of 36.
1 upon 36. Then 3.
1,2. 2,1.
1, 2, and 2, 1. Probability is
2 by 36.
which is okay. 2 by 30.
Sir,
Yes.
sir, can you tell means what the event j is? Means you have written in the third column p of j.
Look, that is the same nomenclature we are following here. Pi is equal to probability at x equal to xi.
Okay, okay.
So Pj is equal to probability of x equal to j. So I have the random variable as 4. How many elements are going to give me the value 4? 1, 3,
3, 2,2 and 3,1.
and 3, 1. No other possibility. So that will be 3 by 36. 5. Tell me directly the probability. I'm not going to write each and every sample space now. 6, 7, 8, 9, 10, 11, 12.
For 5, it will be 4 by 36.
4 by 36. Saurav, now wait, let me call out the names and see who are actually attentive or not.
Fine, sir.
Yes. For 6 is Manas. Manas not there. Sakshi,
3 by 36.
what is it?
3 by 36.
3 by
So
36.
5 by 36. 5 by 36.
This 5 by 36.
Yes, sir.
Okay. Then 7,
6 by
6
36.
by 36.
6 by 36. 8,
7 by 36.
5
5
by
by 30.
Drumil, tell me the possibilities for the set.
So 7 by 36.
Tell me the sample points. I mean, you must have found the samples points, right? And depending on that, you're telling me the probability. Tell me the sample points by which you have got this probability. So it won't have always follow the pattern.
Sir,
Okay,
it will be 5 by 36.
it is
5 by 36 for 8.
5 by
yes,
36.
exactly 5 by 36.
Now it
9.
will reduce.
Now it will reduce 4 by 36, 3 by 36, 2 by 36, and the finally will be 1 by 36. So uh, you can find out the sample points. I'll make the table now. Hence the probability distribution is. Hence so x and p of x equal to xi. So we have the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the probabilities are 1 by 36, 2 by 36, 3 by 36, 4 by 36, 5 by 36, 6 by 36, again 5 by 36, 4 by 36, 3 by 36, 2 by 36, 1 by 36. This is the complete probability distribution. So you can see that what we have done is this is the probability mass function where you have assigned the probability for each and every sample point. Now, the next question, for the following probability distribution of x, for the following probability distribution of x. So we have x is 0, 1, 2, 3, 4. Probability at x equal to small x. This is k, 3k, 5k, 2k, and k. Find the value of k. First one, find the value of k. Yes,
Value of k is 1 by 23.
values is didn't understand what you said. First one. Find the value of k. The other one, find probability of x greater than or equal to 2. Probability of x less than 3. And probability of x less than or equal to 1. Yes.
Sir, 1 by 12.
K is
1
1
by
by
22.
why 1 by 22?
No, sir. No, sir. 1 by 12.
1 by 12.
Okay, 1 by 12. Why 1 by 12?
Sir, addition of all these, it must be equal to 1, so that's why.
Exactly. So summation pi, I is running from 1 to n is always 1. So this gives me k plus 3k plus 5k plus 2k plus k is equal to 1. So that will be 12k is equal to 1, which implies that k is equal to 1 by 12. Now, probability of x greater than or equal to 2, which is nothing but probability of x equal to 2 plus probability of x equal to 3 plus probability of x equal to. Put the values, tell me the final answer. X greater than 3 will be probability of x equal to 4.
2. 2 by 3.
The answer is 2 by
2
3
by 3.
exactly. Yes. Probability of x equal to 4. Oh, sorry. X less than 3, 0 plus probability of x equal to 1 plus probability of x equal to 2. Which is
3 by 4.
3 by 4. And the last one, x equal to 0 plus probability of x equal to 1. The answer is 1 by 3. Fine. So that's all from my side. So we have done this probability mass function today. The next lecture will see probability density function and some examples depending on probability density function.